record to the computer. So I'm starting to record. Gabriel Carras is also arriving. We still have some people going on. So some people are still joining. So that's what I'm giving some time. Do you mind if we start at 5 past?
No problem.
If some more come. Is that okay?
No problem.
Yes. Okay. So actually, it's not so bad. A lot of people.
I'm so sorry, Zach.
Hi, Carla. A few of us from chemistry decided to crash the meeting because it's similar to what we do too. So
yes,
hope that's okay.
No, go ahead. Go ahead. As long as you don't have any porn or any trolling, we don't mind. You know that there's this Zoom bombing. Anybody doing Zoom bombing is going to be kicked out immediately.
I've heard some physicists suggest that chemists are trolls in general, but I'm not going to engage in that here.
Yeah, okay. So I'm just letting people in. And Abby is going to keep...
Look who's there.
Keep an eye on the people. If they start to do something strange, put them out. But you are more than welcome, and because I know also that this topic is interesting for Sergei's group and Jonathan Tennyson's group as well. That they're very much interested in imaging and how you do these kinds of things. So I don't think we're going to have anyone else joining. So welcome everybody, wherever you're joining from, and I'm really glad to have you here today. This talk is going to be by Zack Dube from NRC Ottawa, and he's going to talk about spatiotemporal imaging of valence electron motion. So very nice to see all of you. I'm switching off my camera and just keep watching and hanging there.
Should I be going ahead then, or?
Yes, go ahead.
Okay.
Go ahead. Go ahead.
All right. Let me just get this going. All right, so everybody can see the PowerPoint now nicely. Okay, so my name is Zack Dube, and I'm here today to talk to you about our recent work on spatiotemporal imaging of valence electron motion. I'm also going to include a few other things to begin with, because I think it'd be a bit silly to just jump into the big picture. I'd like to really take some time and describe how the Coltrims apparatus works first, because I'm aware that many of you will be theorists. So I'd like to go through a lot of the experimental things that we do first, and how the analysis tends to work on that side of the picture. And then I'm going to do a bit of a history on this experiment, and finally show you the results that end up in this beautiful picture of a wave packet motion in ion. So just a few things to begin with. I'm from Ottawa, Canada, and on the right here I'm showing the beautiful main building of the National Research Council Canada. Or the original building, I should say. It's a very old building for Canada, 100 years old. Maybe not so much for here, but it's a lovely building, lots of beauty in there. And we'd be more than happy to welcome anybody who'd like to come visit, except hopefully in better times than this. If you do come visit, I'd like to warn you about your itinerary. One big mistake that Europeans tend to make: do not try to plan too many cities in one trip. You cannot travel to both Ottawa and Vancouver by car. It will take you far too long. It's a long drive, several days. So don't do that. A few things about Ottawa. We always get asked the question, what's the weather like? Well, in the summer, it's beautiful. The trees are blooming, the flowers are beautiful. You know, we get lots of nice sunshine, and we have record temperature highs of 38 degrees Celsius. However, in the winter, it's a different story altogether. We have a lot of snow, and this is what it might look like on a heavy snow day. forget about going anywhere on a day like this, because we get over 50 centimeters in a 24-hour period, and that doesn't mean that's all the snow. I believe the record one snowfall is somewhere around 1 meter, so forget about it. Just let the army of snow trucks come and clear everything away. And yes, it's cold, but not on these snowy days, actually. Our record temperature low is -39, and that's not even the worst part about it, is that it really just feels bad when it's windy, and it can feel like it's -50 or so. So we get very big temperature swings, about 80 degrees from summer to winter. And it's really quite, you have to have a very unique wardrobe to live in Canada. So the last thing I want to mention about Canada is we often get asked about the wildlife. So I'm going to take a moment to talk about bears. This fellow here, the black bear, is a very harmless bear. Just don't get between it and its cubs, and it'll leave you alone. Sometimes we even get them into our cities. Recently, one was seen in the market area, and it was just shooed away fairly successfully by animal control. Then there's the grizzly bear. Don't mess with grizzly bears. They're big, they're angry, they're scary, and you can see them sometimes on hiking paths. Typically, you would want to bring a bear whistle or bear mace if you're a very serious hiker in deep woods areas, but they don't tend to come into the cities very often. And finally, the polar bear. This is a big no-no. Stay away. They will happily eat you. In fact, in some northern cities, it is common courtesy to leave your cars unlocked so that you can hop in if you happen to see one. Okay, so that's enough about Canada and bears. Let's get into some science. So I hope to have this slide on for quite some time. This is the Coltrims apparatus. And Coltrims stands for Cold Target Recoil Ion Momentum Spectroscopy. And the idea behind it is to get a full 3D momentum picture of an ionization event. So in order to do this, we need to do a number of things. So the first thing I'll talk about is the gas. So the idea here is we hook up a target gas to a jet, which has a nozzle of about 10 to 30 microns typically. And this will allow us to shoot a gas into the chamber. And the skimmer will allow us to make it a very fine molecular beam. Additionally, we cool down the jet with a cold finger, which is just attached to a helium compressor to bring it down to temperatures of around 100 Kelvin, reducing the thermal bumping around of the molecules. And the skimmer, additionally, after passing through, it'll undergo supersonic expansion and reduce in temperature even further down to about 10 Kelvin. And this will really reduce the momentum, any momentum we get that we would see from temperature. So in order to see such a jet, the chamber has to be, which is not pictured, it's a big metal monstrosity, would have to be pumped down very low in order to see this thin molecular beam from the jet. And in order to do this, we employ various stages of pumps. The first one is called a roughing pump, which is just a mechanical pump that creates a pressure differential and kind of sucks the air out. And that's the first stage. This will go down to about -3 to -4 millibars. The next stage is going to be with a turbomolecular pump, which is still mechanical, but it's a spinning blade. It doesn't suck. When molecules hit the spinning blades of the turbo pump, they get ejected from the chamber through the pump. Finally, the remaining pump that we make use of is a cryopump, which is a trap that we keep quite cold. It's attached to the same helium compressor that we use for the jet, in fact. And whenever a molecule hits this, it's frozen and trapped and does not contribute to the background of the Coltrims anymore. And when we combine this with baking techniques, such that after we've opened the chamber and done any work there, we bake out the walls so that any background gas that might be attached to them detaches when we bake them rather than during our experiment, and gets pumped out. Ideally, we can drop down to pressures of -10 to or -11 millibars, ideally. And this will allow us to see our gas jet over the background. And you'll see in some of the graphs that I include later what the background in the jet will look like. Next, we actually have to do the ionization. And of course, there's a lot to talk about here, but I'm just going to skip most of the laser stuff and say we put an ultra short pulse into our chamber. And it goes in along the y-axis. I think you can see my mouse, yeah? Okay, it goes in along the y-axis and hits a parabolic focusing mirror and gets reflected back onto the gas jet, ideally. Of course, this is a bit of a pain in the butt to align if you don't know how to do it, but this is all experimental stuff. The size of the focus is approximately 100 to 200 microns in length and about 10 to 20 microns across, but it of course depends on the size of the beam that you're using. So when you've aligned the gas jet and the laser so that they intersect in the focus, the target will be ionized usually by tunnel ionization. So in this case, we're going to be left with a positive ion and a negative electron. Now, in order to distinguish these, we have these spectrometer plates throughout the chamber, and they put a constant electric field throughout the chamber, and this will accelerate ions in one direction and electrons in the other, such that positive charges in this case will fly up and negative charges will fly down. And if you consider the differences in mass between ions and electrons, you'll note that electrons are much, much, much smaller, so they will hit the MCP considerably faster than the ions. If we were to do this, we would not get very much resolution in the X and Y direction. As you can see, we kind of have a parabolic trajectory. Oops, I've gone too fast for the ion to the MCP, but the electron has a curved one. And we employ these magnetic coils to make the electrons rotate along their trajectory to the MCP where they're detected. And the reason for this is because otherwise they would fly too fast and we would not get any resolution in the X or Y direction. So the position on the MCP gives us the X and Y information, and the remaining dimension in Z is given by timing. So what we would do is we would include a photodiode somewhere in the laser path, and this would give us a time zero effectively. And we time the difference between when the laser strikes such a photodiode in the laser path and when the charged particle is detected on the MCP. And by calibrating the difference between this photodiode hit and the hit on the MCP, we can tell how fast it took how much time it took for the ion or electron to hit the plate, and we can calculate the momentum from that. So I'm going to show you a bit about what such data would look like. Let's look at a typical ion time of flight spectrum. So what we're going to do is we're going to look at the time of flight along the x-axis, and then we're just going to look at the number of counts along the y. So it's a one-dimensional plot effectively, and we can learn a lot from this particular plot, actually, much more than you would think. So each of these peaks in the ion time of flight spectrum represents a different species of atom or molecule. And this is because they all have different masses, and the different masses will take a different amount of time to fly to the detector. So in this particular experiment, we used argon, and typically we always see the highest peak for whatever gas we're using. So we can identify this peak as argon plus, and we can identify some of the background peaks right away as well. So the next two we can do are H2 plus and H plus, which are typical background ions we'll see, as well as water plus, which we always have a bunch of in our chamber. No matter how much you get rid of through pumping, you'll never be able to get rid of all the background. Additionally, we will see argon 2 plus, depending on, of course, the conditions of the laser and how much intensity we use. So in this case, we see a fair amount of argon 2 plus. And we also see N2 plus and O2 plus as a broad shoulder over here. These 3 little peaks and 4 little peaks you can pretty much ignore. Those are just leftover things from when we were servicing our jet, HCl mostly. Excuse me. Now, if I were to add an additional dimension to this, we would be able to see a lot more information. So I will show you the ion TOF versus Y spectrum. So this is effectively the Z direction, and this is the Y direction. And you can see all these peaks line up. I'm sorry that the plot is a little bit stretched. It's very difficult to make 2 of the same. But it is indeed the same thing. So you can see the argon plus, very narrow peak. It's this small bright spot here. The jet peaks are always very, very narrow, whereas the background is always very broad. So you can see the broad water peak. This is the shoulder of the argon. This is background argon plus. We have N2 and O2 plus, and you can see small little peaks that are from the jet. And the jet is in fact actually on a negative slope in the y direction. And the reason for this is because the jet is actually moving over time. So we have additional momentum that will be compensated for in our analysis from the movement of the jet in the first place. So when we take a look at the argon plus, for example, if we want to look at a momentum spectrum, we have to pick a narrow time of flight and we have to calibrate its position. And when we do that, we get a plot that looks something like this. In this case, most of the polarization is along the y direction. And you can see that the ions gain momentum along the y direction, and they have a small spread in the z direction due to tunneling. Although admittedly there is a little bit in the z direction, but I don't want to talk about that in this particular talk. So this is what a typical linearly polarized pulse would look like, the momentum from such a pulse. I just want to include another example, except using mostly circularly polarized light. This, for example, was done on D2, not H2, but deuterium-2. And you can see that there's no more argon peak. There's still small peaks in nitrogen and oxygen. Those are probably a little bit in our canister. But it's mostly background, except for where the D2 and the D plus are. And when you look at this in the y direction, we can see a wealth of information again. And I've actually just cut it so that it's mostly from about 1,000 time of flight to about 4,000 time of flight this time. And you can see here we have a D2 peak at about 3,200 nanoseconds. And this big peak here is a D plus peak. And this, you see 3 different rings that will all correspond to differing dissociation pathways, with the most energetic being Coulomb explosion, where we actually have 2 D pluses pushing against each other, giving each other energy, because it's been doubly ionized. You can also see in the background, we have H plus on the left, and we have even some HD peaks, HD D plus peaks in the jet that come from non-perfect deuterium samples. So looking at the electron, and if you look at the ion momentum, this is what it would look like. This is once you've calibrated it. Of course, I didn't do a great job on this. This is my apologies for this. It's not centered at 0 and it's not rotated. I see Andre is grinning at me. But the ionization momentum here looks like it's not a very circular pulse, because we would see equal momentum all around. It's equal likelihood to get any particular vector from a circularly polarized field, whereas in this case you can tell that where's my mouse from? In this direction it's stronger because we get more ionization probability along this direction. Moving on, we can look at the electron time of flight, and this is what the electron time of flight looks like against the y direction, and we see in this case a very important feature, the rotation of the electrons in the magnetic field. And at this point, we actually get no information about X and Y, but it's still a good, we actually in fact need to know about these nodes, because otherwise we cannot calibrate our electric field and we cannot calculate the electron momentum. Now, unfortunately, you see that there's a lot of electrons in the first node here, and that means that we're not going to have very good resolution on our data. And that's okay. This isn't really a big data set here. I just thought it would be a good example. So when we look at the actual momentum that we calculate from these plots, we see that we, for the most part, get this circular example, because the electrons get the circular momentum as well, except we see an unfortunate node in the data around 0.5 atomic units in one direction. And this would also indicate usually that it would be elliptical, because you can see a bunch of ionization here, and there would be some here, but we lose a lot of our counts when we have them in the rotational node. So the last thing I want to point out is that momentum conservation is a very important concept in Coltrims, both because it helps us calibrate our data. On this plot, we have the ion momentum for argon plus and the electron momentum for argon plus plotted against each other. This should form a nice -1 slope, because we have conservation of momentum in this case. Well, all cases. And in fact, this can be very, very useful if we have a multiple ionization event. For example, if we have argon 2+ and we only detect 1 electron, we can reconstruct the second electron by the information that we have from the argon plus and the first electron. So it can be very useful if we don't detect both electrons exactly. Moving on, let's discuss a little bit more about the history and the goal of our experiment. So our goal is to find a recollision-free method to image electronic dynamics immediately following photoexcitation. And previously unaccomplished is directly imaging bound electron wave packets on a femtosecond timescale. And we can achieve this in a spin-orbit wave packet in argon using a 3-pulse scheme to avoid contamination. So what do I mean by contamination? Well, if we have two kind of ionizations back-to-back, so when I say back-to-back, I mean on a femtosecond or even to picosecond timescale, we can't distinguish which one is which in our detector. And this is because we detect our electrons on a 100 nanosecond timescale. So in order to tell which one is which, we'll have to employ an additional third pulse that we'll get to later, and I'll discuss that as we go. So the first experiment I'd like to talk about was done by Moritz Meckel in our lab in 2008. And this is an experiment which does not, in fact, measure a wave packet on an ion, but it measures a wave packet on a neutral. It's a pump-probe experiment, so we have an alignment pulse that comes in first, and this pulse will excite a rotational wave packet on a linear molecule, in this case either N2 or O2 are the two molecules he used. And after a certain amount of time, depending on the molecule, the rotational, what's it called? I'm sorry, the word is escaping me. Anyway, so at certain times, all the N2 or O2 will be aligned along the pulse, and at exactly half the period later, it will be anti-aligned, and then it will be outside of it'll be on the plane that does not contain the polarization vector. And in this case, we send a probe pulse, which measures the excited wave packet, both at the aligned and anti-aligned states. And we measure these two momentum distributions that are shown here. And you can tell immediately how obvious the difference is. It's very striking. And no, of course, that's just a joke. We have to make use of one of the most powerful techniques we have at Coltrims' disposal, and that is the normalized difference, because we have, you see, it's a very vastly logarithmically scaling diagram. You have to kind of normalize the counts on each plot and subtract the difference, subtract one from the other, and then we'll see the difference between the two. And when you do so, for oxygen, the anti-aligned and aligned differences look like this, and for nitrogen, we have this picture. And when you do the theory and look at the contribution from the HOMO, in each case, you see that the symmetries are very, very similar, and it looks like a very good representation of the HOMO. And we like to call this technique the molecular STM, where in a normal STM, you would move a tip over a solid, and moving the tip images a different spot. With the molecular STM, we have the rotation rather than the tip, which moves, and the laser is what does the ionization. Moving on, let's start talking about a SpinOrbit wave packet. So Gulielmakis is, to my knowledge, the first to show this experimentally in an attosecond transient absorption experiment, at least in live time. And what happens here is he takes a krypton atom and uses a mid-infrared pulse to ionize it once into the 4p-1 state, where the 1/2 and 3/2 orbitals have what's a very, very narrow energy difference, and both can be excited at once. And what this does is it creates a wave packet that oscillates between the characters of the 1/2 and the 3/2. And the oscillation speed of this wave packet depends on the energy splitting. The larger the splitting, the faster the wave packet oscillates in character. So in this case, once it's in this state, Gulielmakis used an XUV pulse, which further excites it from this 4p state to a 3d state. And depending on which state it is in, or which character it's showing when the XUV pulse arrives, it will preferentially absorb more or less, because it's more likely for it to go from the 3/2 to 3/2 than it is for it to go from the 1/2 to the 3/2. And you can see this, it's the longest arrow. In this plot here, we're showing the delay versus what they're showing is the cross-section on the y-axis. At 81, approximately 81 EV, which is the big arrow, you see that there are peaks and valleys, whereas at 80, you see it's just a narrow, it's a flat top. You don't get any variance. So if you zoom in on this particular peak and look at the absorbance over time, you see that when the character is 3/2 to 3/2, the absorbance is higher, and when it's 1/2 to 3/2, the absorbance is lower. And this oscillates with a period that's exactly expected by the SpinOrbit wave packet separation, the energy separation, and you can see here what the phase might look like, what the orbitals might be doing as this happens. You can see it oscillate from a peanut to a donut character, and I'm going to keep talking about these peanuts and these donuts, so please mark their shape, because these are what we've used in ours. So we've tried to reproduce this in our lab a little bit later. Avner Fleischer did some experiments that didn't work out ideally. He did do some later that did work out. This is electron data, I believe. And we just did not get enough statistics on this to really image the wave packet as it changed. This is in neon, and it's a much longer splitting, or sorry, a much smaller splitting, so it's a longer oscillation. And Avner did go on to do some results in argon that I'm not going to include in this talk for the sake of brevity, but he did show some really nice results with ions. So I'm just going to stick to the electrons, but if you'd like to go look at that, I suggest you do. So the last paper I'd like to talk about before ours is by Fechner in the group of Robert Moshammer and Thomas Pfeiffer. And this one is on argon, which is like what we use. And the idea is you come in with a pump for argon neutral and ionize to argon plus. And again, we have this 3/2 and 1/2 splitting. And the energy is such that it takes about 23.3 femtoseconds to oscillate in character between a donut and a peanut shape again, where the hole is. And eventually we come in with a probe, and we can vary the timing of this probe so that we test it at either the 3/2 or the 1/2 or in between, and we can measure the likelihood of ionization. So that's what Fechner did. You see that when the peanut orbital is occupied, you have a higher chance of ionization because it's along the laser polarization, and when the donut is occupied, you have a lower chance of ionization. And if you look at the perpendicular momentum distribution that they found, which is along this axis, corresponding to and then on the y-axis they have the timing. So you go from a 0 cycle to 1 cycle. You can see that these are, I should make the point now that these are the momentum orbitals, by the way, and you can look at the perpendicular momentum as how far this way it goes. So the peanut orbital has a lower perpendicular angular momentum, and the donut has a wider perpendicular momentum. So you can see that it oscillates from low perpendicular momentum to, high perpendicular momentum to low perpendicular momentum to high perpendicular momentum again as the cycle changes. So this was a really impressive result, particularly since they didn't do anything to deal with the contamination. But we actually proposed an adjustment to this experiment that will give us, I think, a much better result and a much more comprehensive result. And it is more valuable for the future, I think. So here is our scheme from our experiment. So we're going to use a three pulse scheme, a pump, probe, and deflect scheme. So the pump and probe are as normal. We have a pump that comes and excites from argon to argon plus. Not excites, ionizes from argon to argon plus. An additional probe later that ionizes a second time. However, the difference is we have a mid-IR pulse that is along the perpendicular direction to the polarization of the pump and probe. And this IR will deflect the electron. It will give it an extra kick in the direction of, in the X direction. So if we look at the distributions, we've seen this distribution already. I've shown it for what a linear pulse looks like. It's mostly, we have a distribution along Z in this case, and it's centered along X at 0 with a narrow distribution. Now, if we were to look at just the probe and emit IR deflection and not consider the pump, we would see the same thing, except the distribution has been kicked out from px 0 central, and now we're centered at around minus 1.5. So you can see that electrons that have been excited in, ionized in this spot have been moved over from px 0 to about minus 1.5. And if you look at all three together, you see most of the distribution is still around 0, and that's because it's easier to ionize the neutral than it is the cation. But anything ionized by the probe gets kicked out to the negative side of the distribution, and we can just use these electrons for our results. And when you do that, and you do, so just to reiterate, we can tag the events. Anything with, if we have 0 net momentum, we know it's in the X direction, I should say, it's from the pump only. And if we have too much net momentum, it's from the probe only, because it's been streaked too much. So only the middling electrons, which have, let's say, 1 unit of momentum in the X direction, are from the pump and the probe together. So in this way, we can get rid of double pump and double probes as well. So when you do all this and you look at the remaining distributions, you can again see the very nice, sorry about that. You can see a very nice oscillation in time when you as you vary the delay of the pump and the probe. And the you can in fact look at the momentum space orbitals. This is from above, so you can see the peanut here. It's a little ball in the center, and as you increase the time delay, it transitions into a nice circular donut with a gap in the middle. And it's very similar to the theory that you would see if you look at the orbitals. And similarly, the real space picture, take this with a grain of salt. This is a Fourier transform with a flat phase, but it still looks very similar to what you would see from the theoretical real space orbitals. And that's very cool. So similarly, we can look at the longitudinal distribution. And again, just to emphasize, this is all normalized differences. If you look at the left side versus the right side, where it's been symmetrized and the left side is on one part of the cycle and the right side is on the other part. So you have the m equals 0 on one side, the m equals 1 on the other side. When you take the normalized differences and look at them, you can see a major difference in you see the peanut along the X, along the center of the Y, and then the donut wrapping around it. And indeed, we can make a full 3D comparison. And I would like to say that this harkens back to Moritz-Meckel's work in 2008, where they did a molecular STM of oxygen and nitrogen molecules, except here we're doing it on a cation rather than on the neutral. So, in conclusion, I would like to say we've looked at a Coltrims and some basic data analysis. We've reviewed a historical perspective on observing bound electron wave packets, and we've discussed our recent method to resolve said wave packets experimentally and without contamination. And I'd like to thank everybody, particularly Dr. Andre Staudte, who's here on this call, for being a great boss, and Dr. Matthias Kubel, without whom much of this work would not have been completed. And I'm very thankful to the both of them.
Thank you for this really nice talk. Now, are there questions? Are there comments? A. Johnson would like to ask some question. Would you like to ask it yourself? So please unmute.
Oh, I was actually just applauding Zach, but I would love to know what a cation is.
A cation is a positive ion, is it not?
I think it's pronounced cation.
Oh, come on. Alan would give me sass about this.
Yep.
Did you? I didn't hear that. Did you actually say cation?
I did say cation. You don't like cation?
Good. Okay, good. That's hilarious.
So does anybody have a question here? Come on. Anything in the chat?
No, that's okay. I'm glad I explained everything very well.
You explained everything very well, but I mean, I think it would be normal to have questions, right? Barry, go ahead.
Hi, thanks for a very nice talk. I'm a naive theorist, so this is maybe a silly question, but that's fine. So you've shown that you can excite specific wave packet states in atoms and molecules. But as a chemist, I was wondering, is there any plans in your apparatus to then use these specific states to do targeted chemistry, like state-to-state scattering?
This is a great question. Ultimately, that's the goal, but for us, it's a little bit beyond us. I mean, we can certainly work with a chemist to maybe think up something, but I think for us, like looking at the pathways is ultimately the goal, and then it's up to the chemist to kind of decide how they would like to use this. And maybe Andre has some bigger picture thoughts than I do, but
think about Tian.
So, any comments?
I have a
Yes,
comment.
go ahead.
I was saying, Zach, you could answer this question by thinking about Tian's project.
on bromine.
Yeah, that's a chemical reaction.
Sure. Okay. So you can look at certain things like the breakup of bromine, like, but this is certainly. I guess that's a good point. It depends on how deep the chemistry you want to look at is. For example, if I were to show the, if I go back to the H2 data, looking at this picture right here, you can actually isolate each of these processes, and each one of them is a different dissociation process. And you can learn a lot about how H2 might dissociate given the timing information and how you excite it and ionize it. So in a way, this is, I guess, a chemical reaction. I guess maybe I'm thinking too big. And there are many papers on H2, and I highly recommend reading a review. Very interesting stuff.
Thank you.
Since we're on this slide, can I actually ask what? Okay, so I've looked at a fair bit of Coltrims data in my time, but this one seems odd to me. What's the transformation that's going on here that's causing it to have this sloping or like almost perspective shape?
Oh, that's a good question. I'm not sure. I'd have to take a look at, this was done fairly quickly. It might be a cut. It might have to do with just the edges of my detector. It's a fairly, like if we look at the, yeah, it might just be the edge of the detector.
Okay, it just looks like you've like drawn it in perspective almost. I was wondering if something particularly interesting was going on.
No, I don't think anything interesting is going on here. I think it's just, I will admit this was hastily done.
Okay, but you think it's some flying off the edge. Fair enough.
Yeah.
This is the detector acceptance angle for fast velocity ions.
Yeah.
It's just like it comes out looking so much like you've done like a perspective transform. It's incredible. But okay, cool.
Maybe I have a question.
Go ahead. Yes.
So can you imagine how to, or let me first ask, what is special about this? Maybe make it clear again. What is special about this method to have the streaking field on there? What does it? How does it differ from the old Meckel, the 2008 experiment where we saw just the static electronic structure? You mentioned wave packet, but it was a static.
Yeah, well, certainly the difference is that we're observing the movement of the wave packet on an ion rather than on the neutral. So it's a two electron process is the big difference. And previously, one electron is much easier to deal with, way easier to deal with than two, for a multitude of reasons. The first is what we're pointing out here is that the results get contaminated by the electron because you cannot tell which one's which, not even for the normal reason with electrons, just because they get ionized at roughly the same time. And then you cannot tell based on the detector which one is which. So because we're detecting them on the scale of femtoseconds to picoseconds time difference, and we're detecting, sorry, we're ionizing them on the scale of femtoseconds to picoseconds time difference, and we're detecting them on the scale of hundreds of nanoseconds, you can't tell them apart. And so this method pushes one to the side effectively. So you have an electron getting detected here and an electron getting detected here.
Yeah. So can you imagine where this could be useful as well? I mean, for instead of saying measuring ions, could it be used for measuring neutrals, having this type of streaking approach?
Sure, I see. I mean, what would the streaking be useful for in such an experiment? That's a good question.
So Meckel's experiment relied on the alignment of the neutral molecules.
Right. Perhaps we wouldn't need to align them to begin with. Is that what you're trying to lead me to?
Yep.
Very good. Okay, so we could skip an alignment pulse in that case.
But what would happen then? So you would do what? You would have still a 2-pulse experiment.
Yeah. So you would have so it would still be pump probe with a deflection, right?
Mhm.
No, you would skip you could skip even the
You need to
skip the
deflect.
pump. Well, it depends on what you're doing, I guess. Yeah.
So if you don't have to align the molecule, you have to kind of get the molecular frame out somehow, right? And how would you do this in a regular experiment?
Well, you can do this in the post processing. You can convert things to the right frame, right?
So you have to dissociate the molecule.
Okay. Yeah.
Yeah.
So you can do it without dissociating the molecules, which you
Really dissociate it afterwards with a Coulomb explosion, for example. Or so. And in the Coulomb explosion, you create more electrons, which then again would contaminate your first electron that you're interested in. But now having the streaking field, it allows you to throw those away.
That makes sense. Yeah.
So one question I would have, you have some kind of pump probe experiment, and you are looking at some wave packet that is moving. So you needed somehow to create a coherence per position of states to be able to observe that. So how do you account for these phase differences in this coherence per position?
So how do we account for the phase difference between? Yes. I mean, the phase difference is what we're measuring effectively, right?
Yeah, but you had some theory as well. You showed like theory and experiment.
So how did we do the theory? I will admit, I am not 100% sure about how the theory was done on this. I didn't have a hand in it, but I believe, for example, if we wanted to look at this theory here, I believe this was just done using the games package, and he did a full ionization and propagation with games to generate this this image. So I'm not sure how I've never used games myself, but I'm not sure how. So I would imagine maybe he did the difference between like the phase difference by hand in games. So he took one orbital and kind of propagated it by hand between the two. I'm uncertain, to be honest. But
okay, but you're still using the single orbital picture or a combination thereof.
Yes.
Yeah.
Okay. Okay, other questions? Ab, you want to say something? Sorry. No? Is okay? Other questions? A really interesting talk, and thank you also, Andre, for joining. Cornelia, I want to say something. Go ahead.
Sorry. No, I had a question, but if we're out of time, then I'll ask it another time. It's also good.
That's all right.
No, it's okay. We're supposed to go up to 5. It's 5. You have time.
So one thing that I was wondering about when I was looking at your explanation of the streaked or shifted data, it reminded me of, I did a theoretical PhD in an experimental group. So I have this kind of half knowledge about experiments, which is and one thing that I remember very clearly was that they always tried to have the jet direction not in the same direction which was the main observable to take out the data afterwards. And I think your IR, the deflection, is along the X direction, which is, if I remember correctly, the jet direction. So I was wondering what
this
the
is
thought
actually
process was for this
an excellent
choice.
observation. This is a problem with the Germans. The man who did the main analysis used a different coordinate system than I did in my introduction. And this is perhaps something I should have mentioned. So the X direction is the time of flight in our experiment.
Right. Okay.
In this experiment. So we get the highest resolution along the time of flight. So this really helps us. Were we to do it the other way around, it would not be as distinguishable.
Yeah, exactly. I was wondering because
Yeah,
we
no,
tried
that's
to
an
keep
excellent point.
Yeah.
Thank you.
So any more questions? Also, if you want to chat with him apart from physics, feel free to do so. It is quite informal. It's an informal setting. So we can conclude, or we can stop sharing, or if you would like.
Sure, I'll stop that.
Yes. So everybody, welcome thank you for joining, and you're welcome. And if you want to have a chat with him, and if you're intimidated because it's gonna be on YouTube, I can stop the recording as well. So very interesting talk. And what would be for you the next step then? Because you are looking really at motion of electrons.
Yeah, I think Andre has some.
You said you're stopping the recording?
Yeah, do you want me? I can.
Yeah, we have a super secret project to talk about.
Yeah.
Okay, so 1, 2, 3.